If you want, you can open up to this week for in-class assignment. Can anyone, I just want to make sure, can everyone like do it? Because we had some issues last week. We still have those issues. Or can you guys even see this? I guess you can start there.
I can see it, yeah.
Okay. Cool. So we can review last week. So last week we went over like TensorFlow. And essentially what we learned is that it's a machine learning package that allows us to utilize what we learned 2 weeks ago, which is linear regression. And if you remember what linear regression is, that's essentially finding a best fit line for sets of points, right? And from there, we learned what loss is, which is essentially our error. And we learned like minimizing our loss can create the best model possible, right? And so here we did a bunch of NumPy stuff. We did pandas as well. And then we went into here and we like did our own, used an actual data set. This actually down here, we used an actual data set. So this California housing data set to use linear regression and see whether we could create a good model.
So at the end, I kind of got confused. It said like what would make the best feature, and I just thought feature was a random word you were using, and I don't know what that is.
Oh, okay. So feature in machine learning is synonymous with like your input. So you can have, if you remember,
feature.
Can you say that again?
But like, what makes a better feature? Because it said that the one with 0.7 was a better feature, but I was confused because I thought the one with 0.9 would have made a better feature because it was bigger.
Okay. Yeah. So I assume what it says here. Wait. Actually, Is there one 0.9? Oh, right here. So total bedrooms, I assume, or total rooms to total bedrooms.
I think it was total rooms to total bedrooms.
Yeah. So this one right here, I did highlighted. So it says here that median income correlates 0.7 with the label median house value. So I think you were looking at the wrong, you're looking at the wrong thing. So even though like total bedrooms and total rooms have a high correlation, because that makes sense, right? If you have a lot of rooms, then you probably have a lot of bedrooms. But what we wanted to do is you wanted to look at median house value right here, because that's what we were predicting. And since that has the highest, median income has the highest correlation with median house value, that's why it would be the best feature. So you weren't wrong, like in terms of like looking for the highest one. I think you were looking in the wrong column because we were trying to predict that.
So it was supposed to be the largest column, or?
Oh, no. So this is our output, right? What we're trying to predict is our median house value.
Okay.
And these are our inputs right here on the left.
Okay.
So these are the features that we input and try to predict our median house value.
All right.
The feature that has the highest correlation to what we're trying to predict is median income. And we know that because this in this column is the highest value.
Okay, yeah, sure.
And so that's what this solution is trying to say. That's why it's the best feature, because it has the highest correlation.
Oh yeah, but why can't it be something like population and total rooms? Because that's like 0.9. I thought it
Uh,
said like a larger number that was like something that was better or something.
um, I don't think I'm seeing what you're seeing, because in this column I see like the highest, other than like median house value, which is the same thing as what we're trying to predict. Like median income is the highest in this column.
Wait, so why are we trying to do median house value? I thought it was for all of them.
Because that's what we're trying to predict.
Oh, whoops. Okay.
Yeah.
Okay. Because wait, where does it say that's where what we're trying to predict?
Um, I assume it's somewhere up here. Maybe I forgot to actually. If I forgot to put that in, that's on me. Because let me see. Okay, yeah. Yeah, okay. That's my bad. Because like a lot of the code shows like predict house values, and um yeah, that's my bad. Actually, I should definitely try to make these. Yeah, sorry about that. Okay. Is there anything else that people were confused on? Um, yeah. Okay. No, let me move this here. Okay, nothing in chat. Okay. So we can go to our in-class assignment, and I guess we're kind of. I'm sorry about this, but we're gonna kind of throw away a lot of what maybe a lot of our intuition that we learned last week, which kind of sucks. But there's one key like thing that we need to learn, and it's this idea that like low loss is not necessarily an indication of an amazing model. It is in certain circumstances, but in the in the more complex realms of what we're trying to I'm trying to introduce you to, we'll realize that sometimes having low loss might not make your model very good when it looks at new data. And specifically, we call this phenomenon called overfit. We call it overfitting. So I want you to look at like this thing right here, like this graph. And we can see that there are orange and blue dots. So the blue dots are sick trees, while the orange dots are yellow trees. And we don't care about the axes for now. We just care about the distribution or the placement of the dots on the graph in relation to each other. And so as we think, what do you guys think would be like a good, maybe like model for this? Like how would you split up, like make a line that splits up the healthy trees from the sick trees? Like what would it look like? You can just describe it, the like, screen share.
I'm kind of guessing like a around one of the diagonals of the box, like on the top left corner to the bottom right, or something
Yeah,
like that.
yeah,
Oh,
that's a pretty good one.
I
You
was
can see that.
thinking, that it
Go
might
ahead.
be more like those, like temperature graphs. They just take several points over the world, and then they just like draw these blobs around it. I was thinking it'd look more like that.
That's another good one, right? So like I think that was Sophie. If you had a line, it would go from here, from this bottom right corner to the top right, and that would be pretty good, right? You'd get all of these, but you would miss like some of these outliers up here, right? And you'd make some of these sick trees come down into your healthy tree population. But overall, it'd be a pretty good model. Or you could do what Julia said and make like a blob of these orange ones right here, and then the blue ones like right here. And that would be another way, like that would be like another visualization of the same thing. But you'd still keep like these blue outliers in there. And so we can see here that a this is like a model that we can create. Actually, oh, I switched these up. Okay, actually, okay, go down to here. So this is like figure three. So figure three and figure two are mixed up. But here. Wait, did I? Wait, can everyone leave this? Actually, I should do something. Um, mm, mm. I just realized that none of you guys could edit this, which is not what I wanted you to do. And that's not good. I apologize. Um, no. Okay, can everyone go? There should be like a version 2 in there. Everyone should be able to have their own version. Can someone confirm?
Wait, how come there's just like this random orange spike over there that just it doesn't even have any healthy trees?
Yeah, I mean, yeah. So that's like an error within the model itself. But I guess it can continue. Can someone confirm that they can actually edit this file? I just want to make sure. Because there's a coding exercise at the bottom.
Wait, so what does it mean when it says it miscategorized most of the data? Like, what's the new data?
Yeah, so this is like our training set, right? This is like the exact same thing as this, but then we like made the heat map of blue and orange, right? So
So
this is,
I'm able to double click on it, but then it shows me like the HTML kind of version instead of the like other like editing version. I can see like how I can edit the text, but I don't seem to be able to edit the graph.
yeah, that makes sense. Like you can like edit the text in here and it doesn't change anything on my side. So that works.
Yeah.
Okay, good. Um, that makes sense. Like, because these are just pictures. Um, so we have like, so we made a model, and this is relatively low error, right? There's only a couple of okay. So okay. Okay. So we have this training set, and we made a model that like categorizes healthy and sick trees, and it has low loss, right? Because not a lot of the sick trees are in like the healthy portions, even though like even this orange blot, it doesn't necessarily like predict anything because there's nothing in there, right? And all the blue ones are still in the blue area. So it still shows that like this, like to the model, it's still like low loss because there's no error here. Does it make sense? Like there's nothing, like the boundary is still there between sick and healthy. But we can see that that sort of like model or like boundary there, when we add more data, ends up being like incorrect.
Oh, okay.
So when
Wait,
we
but
add,
for me, the pictures are swapped.
that was my bad. If you want to fix it, you can go into here. Do you see this like SRC, and you
Wait,
change this C to a B.
I. Oh, okay, cool. And what do I change the other one to? I change it to a B.
You change the B to a C.
Okay.
Okay. Sorry. So we have, yes, we have like this. So when we add more data, and we know it's more data by like the outline, so the dark outlines is the new data, we can see that it really does miscategorize a lot of the data. Like look at this like this orange patch over here that's miscategorized as sick, even though it's technically healthy. And so we can see that even though our original model had a low loss or low error, when we add more data, we end up having a higher error, which means that, and this is a phenomenon we call overfitting. And it's also just a general uh, mistake on our part for making a model that doesn't generalize or make or is essentially too complex. So as we see here, an overfit model gets a low loss during training, but does a poor job of predicting new data. And so the question we have to ask ourselves as machine learning scientists is that how can we trust that it'll make good predictions on new data? Or when we make a new model, how do we make sure that it makes good predictions on never before seen data? And so, as we'll see, overfitting is essentially caused by making a model more complex than necessary. And so attention, or I guess like a thing we have to balance as we make models, is creating a model that fits the data well, but also fits the data as simply as possible to avoid overfitting. And the real problem with this is that your model only can ever see your training data set, and it obviously can't see data it's never seen before. So we have to make sure that it fits well in our current examples and examples that it sees in the future. And so I go into, in this text at least, this idea of Occam's razor, which is essentially making a less complex ML model, the more likely that it is to that the less complex an ML model is, the more likely that a result is not just because the training data is the way it is. But yeah. And so there's just more stuff. But the way a model is able to generalize on new data is based on two things, which is the complexity of the model and the model's performance. And so when we meet, what do we mean by complexity, really? We know that these blobs of 2D prediction is more complex than just a line of linear regression, right? So that's what we mean by complex. So our predictor could be a line, which is less complex than these blobs of 2D space, which is less complex than like a 3D polygon that wraps around our dots. And so that's what we mean by complexity. And then there's the model's performance on that training data. And so this is a little complex, obviously, but there's an easy way to fix all of this. And it's essentially what we do is we split our data into what we call a training set and then a testing set. So that training set is data that we only use to train the model. And our testing set is data that we set aside for when we want to test our model and see its actual prediction, and see its actual performance on data it's never seen before. And so good performance on a testing set is a good indicator on how it'll see new data in general. And so overall here is our guide to generalization. So if you take notes, you can put these down. We want to make examples that are independent and identical overall. So that means that examples don't influence each other. The distribution of our training set overall is stationary. And we take examples from partitions that are from the same distribution. So that means these dots are always going to be in the same place. We aren't, essentially what that means is that we're not putting outliers into our model. That's what it's saying. We're not putting outliers into our model. That would skew it. So that's what we're trying to say there. Although we do violate that sometimes. So that means we might choose models that are dependent on each other, or we might choose features that are dependent on each other, for examples. So that means that a model might base its choice on ads, in part on what ads the user has seen before, or a data set that contains retail information, like user purchases, which like change seasonally. So the distribution of your purchases would also change seasonally. That's what we're trying to say. So let's get into more like what we mean by training and testing and splitting our data. So, okay, here. So training set, it's a subset to train a model. And then our testing set is that subset to test the trained model. And so this is what it might look like. This blue is your training set, and the yellow is the testing set. And overall, this is your entire data set, like this whole rectangle. And so some key things is that you must have a testing set that is large enough to yield like meaningful results and is also representative of the data set as a whole, right? Because if your testing set is only representative of a small portion of your entire data set, then you might skew your results or make it look like your model is really good on only on certain examples or certain types of examples. Okay. So Sankrit says, or he messages me, where do we get all the data? Well, I guess that's like a question that's beyond the scope of this class. But let's say that you were at work maybe, and your data is just like metadata that the company collects on its users. So that's where you might get data. You can find data or like information or data sets online, and those can be things that you might be able to use. But yeah. So it's not necessarily where you get the data, but I'll teach this. What I'm trying to teach you is how you might like work with your data, I guess. I hope that makes sense. But yeah. So yeah. So when we make a testing set, it's essentially a proxy or a stand-in for new data, even though it's not never before seen to you, it'll be never before seen to your model. So yeah.
So is the training data like more complicated on purpose so that it can do like a better job of testing the actual test data?
I think so. Wait, no, I shouldn't say that. Let me see. Our test, for example. Okay, what is that? I feel like this is switched around, but wow. Okay. So here. So it's not overly complex. The reason why there's just more dots essentially. Like our training data set, as we can see here, our training set is much larger than our testing set because we want a lot of training sets. We want a lot of training data, but we also have to have a small amount set aside for testing. So the amount of dots doesn't necessarily, like I want to make sure that we're not confusing complexity with just more dots.
Wait, so then the training data is more complex, I guess? Is it?
No, there's just more dots.
Okay then. So okay.
So, I mean, to me, it seems like the amount of blue dots on the training data is ratio to the amount of blue dots to the like on the test data is equal to the amount of the ratio of the orange dots on the training data to the test data is equal. So is that just like a increase of the dot sets in the training data to the test data?
Yeah, so that's a good point, right? So the ratio of like blue dots on the test data to the so the ratio between like the amount of our healthy and sick trees is the same between our training and test data. And that's what we mean by having equal distributions, right?
Okay, but then can't the test data be the training data and the training data be the test data? Like, why can't you just swap them?
Yeah, I mean you can,
Okay then,
but
but
like there's just more dots in one of them.
all right,
You
but
want
then why do they have different names?
they have different names, not because so they have different names, not because like this dot has to be like training or testing. It's because you set aside a certain portion of your data for testing. And you just arbitrarily named it test data.
Okay
The
then.
reason why it's called test data is because the model will only see it after it's been trained.
Okay then.
Okay. So yeah, I'll kind of drive it home. So um, when you make test data, you're just like taking a slice of your data set and you're just like setting it aside for later. And you just name that set test data. The actual like values within it don't really matter beyond it being overall similar to what you see in training, or like the distribution has to be similar. That's the only like thing that makes your test data like different. And so here, cool. And so you probably write this down, but you never train on test data. That's kind of like a sin if you're religious, but like if you're seeing very good results on your accuracy or having a very low loss, like it might be that you're actually training on test data. And so here's an example. Let's say you split your data into 80% training and 20% testing, and you see that your model is 99% accurate on both training and test data. I mean, that means that you probably messed up, since you'd expect that your test data will have a lower overall like accuracy, since it's training on data it's never seen before. And so you might realize that some of the training and test data sets have duplicates. So like there's an example that's the same between training and test, and you realize that you forgot to get rid of those. So you inadvertently use some of your test data in your training set. And as a result, you're no longer measuring how well your model actually generalizes to new data. So that's kind of what we're doing there. And so I'll kind of review what we just said. A good way to generalize our models is to split into training and test data sets. And we use that testing data set to see whether our model is good at, is good at like is good at like generalizing to new data. So here's like a playground, I guess. So if you click on this link, you open it up. Hopefully you should see something similar to this. Can everyone like see this? If you click on that link. Can someone confirm? Yeah, okay. So it's kind of like a quick activity, but you can see that here that we have like a model. If you really think about it, like we have features, and then like we just leave these ones in, but we have like a bunch of stuff here, and if you want, you can read this if you want. But this uses like TensorFlow, and it's kind of like a model in like your browser. And so there's a bunch of hyperparameters up here that you could use, but we're just gonna leave it like this. We have features, and then we'll get into this next week. And this is our output and kind of our graph of points. Kind of similar to, it's actually exactly the same as this. But here. And so make sure that this is clicked so you can show test data. And we have this bottom left data set right here. And so what I want you to do is just finish these tasks and see and like try to answer the questions that are here. And you have until, I assume you can probably take like 11:20 maybe.
Okay.
Yeah.
But okay. I don't really get how to operate this thing though. Like, there's
Yeah.
X1 and X2, and what do I click?
Okay. I'll go through task one for everyone. So don't change anything for now. You don't have to mess with anything. Just click on this play button right here. And you should see the loss move, right?
Okay.
Right here. It'll be fluctuating. And as you can see that we'll reset. So this is the test loss and training loss without any training. Like this is just the baseline error. And we'll press this to train the model. And you see that already the loss has dropped from 0.7 to 0.2. And once you get here and you see that, oh, nothing's being changed, right? Like waited another 50 epochs.
Wait, how do I see the loss again?
Right here, it says test loss. It's the numerical value right next to it.
Oh, okay. Mine is barely changing though.
Yeah. So if you reset, right? Like what does it say now? And you press this rewind button.
117, 0.117. 0.117. Okay, yeah, that's better. How come the loss gets like bigger though? Because in the test loss changed from 0.117 to like 0.178, and then it stops changing.
Wait, do you have all the same like things?
Well, I mean, I
Here?
just clicked the link and I didn't change anything else.
Okay. I guess that makes sense. So you have to like reset this. So if you keep on resetting, you'll see that sometimes when it just like randomly starts, it'll start on like a very bad model. Then when you press the start button, you end up creating like a model that's better.
Oh, okay.
So that's task one. And so you can see the delta. Actually, that's the clear thing, right? So you can see the delta between training and test loss. And this is something that we'll try and like make smaller. So here. What I want you to do right now for next is to change your learning rate. So change this value right here. And I want you to notice or see what happens when you do that. Just like click on something else and then run it for reset and then run it for 150 epochs and see what happens. I don't know if you guys can hear this, but there's an owl, I think, outside my house, which is weird because it's 11 in the morning. Where's the dog? But whatever. Sorry. And then when you're done with task 2, you answered these questions right here, you can then move on to task 3. And that training data percentage slider is right here. This one right here.
So am I supposed to start on this model?
What do you mean by start? You can do whatever you want. Like you can use like this learning rate or change it to what you want. Like if you want to like experiment with whatever you want, but just keep the data the same.
Okay, yeah, but is the test loss is the smaller one, like the smaller amount of data, and the training loss is the larger one, right?
It's nothing like that. You can change it to whatever you want.
No, wait. But then what's the difference between test loss and training loss? You said one was smaller and one was bigger, but which one's bigger?
It's so usually test loss is the bigger one, but it's the label we assign to the loss is technically like arbitrary. Like it doesn't have any meaning to it. It's really just like the loss or the error that the model has for data it's never seen before. And that's what test loss is. It doesn't necessarily have to be bigger or smaller than our
And
training
then
loss.
I just change the learning rate and see if the test loss became the difference between the test loss and the training loss got bigger or smaller.
Yeah, that's
But
essentially what you're trying to do.
when you have a smaller learning rate, the test loss is smaller. So how am I supposed to draw any conclusions from that?
So when you have a smaller learning rate, you have a smaller delta between the test loss and the training loss.
Well, you get a smaller test loss if the learning rate is smaller.
Yeah, which is a good thing, right?
Yeah. So, but it just says change the learning rate. So if I change it bigger, it'll get worse. If I change it smaller, it'll get better.
And I guess that's what you've learned, I guess. You can also try experimenting with like your batch size. And that's like, you want to see what like a 30 batch size looks like. I guess the real question for task 3 is, I guess, it's right there. Does altering the training data percentage, like change like the optimal learning rate? It's taking a really long time. So does anyone have any like findings they want to share with us? Share with the class? Or I guess you can just tell your answers. Okay then. Cool. There's a lot of cool stuff in here. But if you just want to ever like see what this looks like, there's a ton of stuff you can change in here. But yeah. You can try doing it on like the spiral. I'm pretty sure this is like a really hard one. Like try and make like a model that's really good with this. But yeah, I think you probably use that. I don't know. But see, you can try different stuff. And so I'll challenge you to make a good model for this spiral data set if you want in your free time. Nonetheless, we can continue on.
So can it like do that heat map thing, or can it only go in like a straight line? Because so far I've only been able to make it go a straight line, like the color separation.
I think that's you have to like remove some features. So like this is kind of a heat map, like this x1 times x2. That's kind of a heat map, right?
Yeah.
So like that doesn't really change anything. I wonder what does. None of these work. Let's see. Actually, okay. But yeah, there's a ton of things you can change. That's kind of a heat map, I guess, if you were thinking about it. But, yeah. Okay. So let's kind of add on to what we've been learning with splitting data. So I guess do we all understand what we are doing by splitting our data into training and testing sets? Just say yes or no, maybe in chat or out loud. And does everyone understand why we split? Okay. Kind of, kind of get the idea. I guess that works. But let's continue that. So here's like a diagram of like your kind of how you might go about training or picking your best model. So you train the model in your training set, and then you evaluate the model in your testing set, and then you tweak your model based on the results of your test set. And then once you found like a good model, that's the one you pick, right? When we mean by tweak, it's just adjusting anything about your model that you can dream up. So that means that in here, like I just did, changing the learning rate, changing activation, which we'll learn later, changing what features you input, changing the ratio of your test and test data. I mean, you can't change the noise, but change the batch size. There's all that stuff you can change. And so that's when we tweak. And then once you pick the best model, that's the one you pick.
So I tried changing the, what's it called? Oh, okay. So I tried changing the percentage of the ratio of the training to. Oh wait, no. Actually, no. I didn't change that. I changed the x1, x2, x2 squared things. What does that do?
So those are just like the features that you input.
Okay.
And those are like the inputs into the model. If we'd go back to here and we have like these things, right? Like longitude, latitude, housing, total rooms. That's what we're doing here, like with x1, x2 squared, multiplication, sign. Yeah, that's what those are. And so, yeah. So we have this, we split into two, but really there's a better way, and that's splitting into three. So you have a training set, a validation set, and then finally a testing set. And this will greatly reduce your chances of overfitting. And so here, our validation set kind of replaces our testing set. So we said same thing. We train on the training set, evaluate the model on our validation set, tweak the model based on the validation set, pick a model that does best on the validation set, and then confirm our results using that final testing set. And so this kind of improved workflow is that we pick a model that does best on the validation set, double check against the test set. And essentially this is better because it creates fewer exposures to that test set. So we can really make sure that that this model is very good on data it's never seen before. So does everyone understand what a validation set is? It's kind of just another set of data that we split our data into. Oh, Carol said, what do you mean by the inputs? What are the x1, x2, x1 squared, etc.? Are they some kind of graph or no, they're features that we input into the model. They're kind of transformations similar to like these features that we inputted into predicting house values. Yeah. Cool. So, okay, let's go back.
So, are we going to talk about what actually would have made it optimal? Because I couldn't figure out what made the training data percentage, what the training data percentage changing actually did.
Oh, this one?
Yeah, like
Like,
task 3 says to change the training data percentage and see what it does, but I can't really tell what it does.
okay. So we change it from 50 to 10, right? And then, actually, wait, let's do this. So we're at 50, and then, okay, let's put this back here. And, okay. Oh, wait. Let's get rid of all these. Then we can reset. And so this is normally what we have, right? And that's our difference. And then let's see if we can go to 10, if there's any difference there. Well, there's not really that much of a difference. Which I guess is, I think that's more a problem with how like not complex this data set is. Because overall, like it's a pretty good line separating these two like distributions. I wonder if like this will change anything, but whatever. Overall, I guess I'll just answer this myself. Overall, when we change the training data set percentage, it should change your optimal learning settings. And usually we never put ratio of 10% for training to test data. It's usually around 80 to 70.
Okay, and then for learning rate, 0.3 seemed good, and then like 0.1, 0.00001 was about the same, but it was a lot slower.
Yeah, and that's just because the learning rate is a lot smaller. Like remember gradient descent, and we
Yeah.
showed that a small learning rate will get to the bottom eventually, but it will just take a really long time.
Uh-huh.
When we picked 0.03, we picked a learning rate that's actually like stepping towards the bottom in an efficient amount of time. But if we choose something like 10, you might overstep that learning rate.
So the question for task 3 says, does altering the training data percentage change the optimal learning settings that you discovered in task 2? If so, why? So how does it change it?
Um, since you have a smaller data set, your learning rate would have to be smaller. And then also your batch size would have to be smaller. I think those are the big things that would make your data set more optimal. And that's because the reason why is just because you have less training data. And usually when you have less training data, you reduce your batch size and you reduce your learning rate. That's the answer to the question.
So if I reduce the training data percentage, then I can use a lower batch size.
Yeah, you should be using a lower batch size. And you'd also reduce your learning rate.
If I make the training data percentage smaller, then I make the batch size and learning rate smaller.
Yeah. Okay. So I guess we'll continue. And so we'll do the same thing. I put it in here, but we'll use the California housing data set to predict median house value. And this actually really consists of two data sets. We have train and test, the training and testing sets. And we're going to create a validation set by dividing the training set into two parts, which is a smaller training set and a validation set. So if you want to do this now, you can run on TensorFlow, load, and then we want to import packages as well. And you want to get our data sets, that, and then run this. And we did this all last week, and run that, and then run that. So that gets our training functions and then our plotting functions. Okay, in here. And so down here, we'll see that we've created a variable called validation split. And that's just like the percentage of how we'll split our training set into training and validation. So here we've set it to 0.2, which means that 20% of our training set will become the validation set. And so if our training set has 17,000 examples, 0.2 times 17,000 will create 3,400 examples that would be part of the validation set. And the rest, which is the 13,600, will be part of the new training set. And so the question here is, if the data in the training set is similar to the data in the validation set, then the two loss curves and the final loss values should be identical. Experiment with the two to three different values of validation split and do the different values fix the problem. So if you run this, where'd it go? Up here. So you can see that there's a difference between training and validation. So you have to make these more similar to each other and see whether changing this value right here can help that. And so experiment with just like different decimal values, like 0.5 or maybe 0.4, and see what comes back. I maybe put in chat, say what you found was the best number or decimal number to make these two curves identical or close to identical. And it doesn't have to be like, two significant figures. You do like, I don't know. I don't know if that works, but it should. Okay, so did anyone find like a value maybe that make these like really similar? Actually, I guess I kind of found it for you. But anything? Okay then. Okay, so I found 0.4, which is around half of training of your training set going to validation, which really isn't very good. Usually you'd want that to be like 0.2. And we do 0.2, obviously like they're very not similar. Right? And so I guess here we say, no matter how you split the training set and the validation set, the loss curves differ significantly, obviously right here. Evidently, the data in the training set isn't similar enough to the data in the validation set, which doesn't seem correct, but it's actually like a problem. That's
I mean, I got them kind of close with validation split of 0.5.
yeah. Yeah, so I guess this was wrong when I was writing this, but when you have like 0.2, which is what we really want it to be, there's like a big difference between the two. And so I like to say 0.2 because it's a good like percentage point where like most of your data is still going to training, but there's still like some amount that's just set aside for validation. I mean, yeah, 0.35 works. I don't know what I was really doing with text too. But if you want, you can like look at these two tasks. So yeah. So what I say here is that if you type in, if you guess if you run this, you get the first 1,000. We can see that our training set is sorted by longitude, and longitude influences the relationship of total rooms to median house value. So yeah. So that's why like, I guess that I didn't really see that. We didn't really see that in here. So that's my bad. Well, really, okay. So really the thing you're supposed to get at this is that you're supposed to shuffle your data. So shuffle the examples in your training set before splitting into a training set and a validation set. And so to shuffle, you'd use this. There's on your pandas data frame, you do a function called reindex, and you'd find a random permutation of your indexes, and then you'd reindex your training data set. And then you'd pass that shuffled training data set instead of the normal training data set. And so we can see like the complete thing. We've added this new code right here, which shuffles it, and then we input that into our data set. And so we can see with 0.2 whether there's any difference. There might be, there might not. Actually, they're pretty similar already. You can see it right here. It's 85 to 84. Yeah. How does longitude influence median house value and total rooms? I think because it's sorted, that's why. Like because it's sorted, the model thinks that there's a relationship between. We can just discard this whole task 2 thing. That's my bad. I think I was looking at something else. But okay. And so we realized that after shuffling our original training set, that our final loss for training and validation become much closer. Like when we had 0.2, there was a very large gap like this, but now there's a smaller gap like this, only by shuffling. And then if you put in something less than 0.15, like 0.1, we realize that we don't have a good validation set anymore. So that's kind of the low end. And anything higher is still good. Let's see. I feel like I didn't do something. Okay, yeah. So you can see that when we have a lower validation score, there's still like a measurable or like a visually measurable distance between training and validation. So yeah. And then to finalize this, what we can do now is that we can use our testing data set to kind of put this all, come to like a conclusion and see actually how well our data set works. Because this is data it's never seen before after testing. So let's see. And that. And so compare the root mean squared error of the model when evaluated on each of the 3 data sets. So here we have root mean error is 83 for our test data set. And then let's put this to 0.2 and run it again. Let's run this again. So our root mean squared is 83 for our testing data set. It's 82 on the training data set, and then 81 on the validation set. That's pretty good. And so ideally, right, the root mean squared error on all three sets should be similar. And are they? Yes. They're all similar in our experiments, which is good.
So what is the part on? Okay, so like right after you do testing on task 3, fix the problem, it says experiment with validation split to answer the following questions. With the training set shuffled, is the final loss for the training set closer to the final loss for the validation set? And then I wasn't really sure how to answer that, so I looked at the answer, and it says apparently the validation set no longer contains enough examples. What does that mean?
Okay, so for the first question, after we shuffle the training set, they're closer, right? The training set and validation loss are closer for the same split, right? So when we had 0.2 here, this is what we have here, and this is the graph, right? But then when we have 0.2 on our unshuffled graph, unshuffled data, this is the split, right? So that answers the first question, saying that there is, once we shuffle it, the final loss becomes much closer. And then this second one is, at what range of values does the final loss values for training set and validation set diverge meaningfully? And so we say that when that validation split is less than 0.15, we can see a measurable difference between training and validation loss. Because right now it's like 82 and 81, but if you have something less than 0.15, there will be like a greater separation.
Okay.
And so what that means is that the reason why that happens is because there's just not enough examples in the validation set for us to create a meaningful conclusion or come to a meaningful conclusion about how accurate our model is.
Okay, so like if if the validation split is less than 0.15, then it starts like getting inaccurate.
Yeah, like we can't, not necessarily inaccurate, but we can't use our validation set as a good metric for how accurate our model is. It's kind of like a bad ruler, essentially. If that makes sense.
I think so.
Okay. And do you understand what we did in task 4? We just like used our testing set, and then we just compared all of our losses to see that, hey, they're identical.
Okay, yeah.
So yeah. So in the last 4 minutes of class, I'll just kind of review what we did. So we learned what overfitting is, which is essentially that if you make your model too complex, it won't generalize to new data. So that means that even though it's really good at predicting on data on its training set, it won't be good at testing or like predicting on data it's never seen before, as you see in this thing right here. And our way to fix that is by splitting our model into a training set and a testing set initially, as we learned, where our training set is the data that the model sees, and then our testing set is kind of our way to, it's kind of like our metric on how well it actually works on data it's never seen before. And then we went even beyond that by splitting into 3 sets: training set, validation set, testing set where we still train on the training set, and then we evaluate the model on the validation set, and then we confirm our results on this testing set. And then finally, we used a housing data set and saw how this all came together. So yeah, we have 3 minutes left. If you have any questions, you can ask me now. You can still email me, but if you would like, yeah. Here, wait, give me a second. If you would like, you are free to go. But yeah, any questions, ask me. See you, everyone.